A modern airliner rests on the tarmac. Sunlight glints off its massive wing. It weighs over 400 tons. A city block of aluminum, composites, and wire. Yet in a few moments, it will climb effortlessly into the sky. It will cruise at over 500 miles per hour. It will carry hundreds of people across an entire ocean. All of this is made possible by the machines hanging beneath its wings. They are the most powerful, most reliable, and most complex mechanical devices ever built. They are modern jet engines. But the story of how they were created is not one of a single invention. It is a story of rival geniuses, of catastrophic failures, and of a relentless quest to master the fundamental forces of nature. This is the blueprint for the engine that shrunk the world. And it reveals how jet power really took flight. For most of aviation's early history, flight was defined by a single object: the propeller. It bit into the air, pulling an aircraft forward. The power came from piston engines. These were marvels of mechanical engineering. But they had a fundamental limit. As aircraft approached the speed of sound, the tips of the propellers spun too fast. They created shockwaves. They lost their grip on the air. Progress stalled. Flight had hit a wall. A new idea was needed. A truly radical one. In the 1920s, a young British flight cadet named Frank Whittle had that idea. He was a brilliant but difficult student. He saw the propeller as a dead end. He imagined a different way to generate thrust. His concept abandoned pistons and propellers entirely. It was a continuous, self-sustaining explosion. It worked by a simple principle: suck, squeeze, bang, blow. First, a fan at the front would suck in vast amounts of air. Then, a compressor would squeeze that air to immense pressures. The compressed air would be forced into a combustion chamber. Fuel would be injected and ignited. A controlled, continuous explosion. This bang would create a torrent of superheated gas. Finally, this gas would blast out the back at incredible speed. This was the blow. Newton's third law did the rest. For every action, an equal and opposite reaction. The escaping gas pushed the engine, and the aircraft, forward. Whittle patented his turbojet in 1930. The establishment was not impressed. The Air Ministry called it impracticable. The engineering challenges seemed impossible. What materials could contain such heat and pressure? How could the spinning turbine survive such incredible forces? For years, Whittle's vision languished. He struggled for funding, fighting against a system that refused to believe. But across the North Sea, in Germany, a similar idea was taking root. A young physics student named Hans von Ohain had independently conceived of a jet engine. Unlike Whittle, von Ohain found a powerful supporter. Aircraft designer Ernst Heinkel saw the potential. He gave von Ohain the resources and the team he needed. An undeclared race had begun. In 1937, Frank Whittle's prototype engine roared to life in a factory in Rugby, England. It was a terrifying, chaotic machine. But it worked. 2 years later, in August 1939, von Ohain's engine did more. It flew. The Heinkel He-178 became the first aircraft to fly purely on jet power. It was a short flight. A secret flight. But it changed the world forever. The piston era was officially ending. The jet age had begun. The outbreak of World War II transformed jet development. It went from a theoretical curiosity to a military imperative. In Germany, the Messerschmitt Me-262 became the world's first operational jet fighter. It was faster than any Allied aircraft. It was a vision of the future of air combat. In Britain, Whittle's engine powered the Gloucester Meteor. The technology was no longer a secret. It was a weapon. When the war ended, the world was left with this powerful new technology. Its military value was proven. But a new question emerged. Could these thunderous, fuel-guzzling military engines be tamed for civilian travel? Britain was determined to lead the way. The de Havilland Company designed a revolutionary aircraft. The Comet. It was beautiful. It was sleek. Its 4 jet engines were buried in its wings. It flew higher and faster than any propeller airliner. In 1952, it entered service. It promised a new era of glamorous, high-speed travel. For 2 years, the Comet was the queen of the skies. Then, disaster struck. A comet broke up in midair over the Mediterranean. Then another. The fleet was grounded. Investigators launched a desperate search for answers. They recovered the wreckage from the sea floor. They painstakingly reassembled the fuselage. They subjected another comet to immense stress testing in a giant water tank. The cause was shocking. Metal fatigue. The square windows of the comet concentrated stress at their corners. The constant cycle of pressurization and depressurization created microscopic cracks. Over thousands of flights, these cracks grew. Until the fuselage failed catastrophically. It was a brutal lesson. The jet age demanded more than just power and speed. It demanded a new level of engineering, safety, and humility. The American aircraft industry watched and learned from Britain's tragic experience. Companies like Boeing, Douglas, and Lockheed took a more cautious approach. And they had a powerful partner. Pratt & Whitney. Their J-57 engine was a military workhorse. It was powerful, tough, and dependable. It was chosen to power Boeing's new jetliner. The 707. The Boeing 707 was not as revolutionary as the Comet. It was an evolution. Its windows were rounded. Its structure was stronger. Its engines were hung in pods below the wings. This made them easier to access and maintain. It also provided a crucial safety advantage. If an engine failed, the pod structure would better contain the damage. In 1958, the 707 entered service with Pan American World Airways. It was an immediate success. It could cross the Atlantic in under 7 hours. It was reliable. It was profitable. The true jet age for the masses had arrived. The stage was now set for an epic industrial battle. A three-way war for the skies. The contenders were America's Pratt & Whitney and General Electric. And Britain's Rolls-Royce. The prize was dominance of a multi-billion-dollar market. The key to winning was not just power. It was efficiency. Jet engines were incredibly thirsty. Their high fuel consumption limited range and drove up ticket prices. The solution would be one of the most important innovations in aviation history. The high bypass turbofan. The original turbojet was simple. All the air that entered the engine went through the core. It was squeezed, burned, and blasted out the back. A turbofan was different. It had a much larger fan at the front. This fan acted like a ducted propeller. It moved a huge volume of air. But only a small portion of this air entered the engine's core. The rest of it, the bypass air, flowed around the core. It was accelerated by the fan and then exited at the back. This slow-moving bypass air mixed with the fast-moving hot gas from the core. The result was a massive increase in thrust. And a dramatic decrease in fuel consumption and noise. The engine had become quieter and more efficient in one brilliant move. The first major high-bypass turbofans were built for the military. General Electric developed the TF-39 for the massive C-5 Galaxy transport. Pratt & Whitney developed the JT-9D. It was designed for an aircraft that would define the next 50 years of travel. The Boeing 747. The 747 was a monumental gamble. It was so big, it was nicknamed the Jumbo Jet. It required an engine with power and efficiency never seen before. The JT-9D delivered. In 1970, the 747 took flight. It democratized air travel. It made flying affordable for millions. The world suddenly felt much smaller. The competition intensified. GE used its TF-39 technology to create the commercial CF-6 engine. It powered the DC-10 and the first Airbus, the A300. Rolls-Royce, facing financial ruin, took an even bigger gamble. They developed the RB211 for the Lockheed L1011 TriStar. The RB211 was a radical design. It used 3 separate spools of turbines. This allowed each section of the engine to spin at its optimal speed. It was incredibly complex, but also incredibly efficient. The project's costs spiraled. It nearly bankrupted Rolls-Royce. The British government had to step in and nationalize the company. But the engine was a masterpiece. Its 3-spool architecture became a Rolls-Royce signature. It established the company as a leader in engine technology. The blueprint for the modern jet engine was now complete. But the quest for perfection was just beginning. The new focus was on mastering the extremes. Inside the heart of a jet engine is a place of unbelievable violence. The turbine section. This is where the hot gas from the combustor slams into a series of spinning blades. These blades extract energy to power the compressor at the front. The temperatures here can exceed 1,700 degrees Celsius. That is hotter than the melting point of the metal the blades are made from. This should be impossible. The blade should instantly melt and fly apart. The solution is a work of hidden genius. Engineers turn the blades into hollow, intricate structures. Cool air is bled from the compressor. It is forced through a maze of tiny, complex passages inside the blade. This air flows out through microscopic holes. It creates a thin, protective layer of cool air over the blade's surface. The blade is flying in its own personal, refrigerated atmosphere. Then came the next breakthrough. Single crystal casting. A normal metal blade is made of countless tiny crystals. Under extreme heat and stress, these crystals can shift and separate. A single crystal blade, as its name suggests, is one continuous, unified crystal. It has no grain boundaries to break apart. It is incredibly strong and resistant to heat. This allowed engines to run even hotter. Hotter meant more power and greater efficiency. The final piece of the puzzle was the brain. Early engines were controlled by a complex web of hydromechanical systems. They were analog, imprecise, and required constant adjustment. The digital revolution changed everything. FDEC arrived. Full authority digital engine control. It is a dedicated computer system for the engine. It uses a network of sensors to monitor thousands of data points. Temperature, pressure, rotational speed, vibration. The FDEC constantly adjusts fuel flow and airflow. It optimizes performance for every second of the flight. It ensures maximum efficiency. It prevents the engine from exceeding its limits. It makes the engine smarter, safer, and more reliable than ever before. This relentless pursuit of power, efficiency, and reliability has transformed our world. Today, a twin-engine jet can be certified to fly for over 6 hours on just one engine. A system known as ETOPS. It has opened up direct, long-haul routes across the vast emptiness of the Pacific Ocean. An engine failure is now so rare, a modern jet engine can operate for over 30 million miles before needing a major overhaul. That is the equivalent of flying to the moon and back 60 times. From Frank Whittle's impracticable idea, to the catastrophic failures of the comet. From the high-stakes battle between industrial giants, to the hidden genius inside a single turbine blade. The modern jet engine is more than a machine. It is a monument to human ingenuity. It is the invisible blueprint that connects our continents, our economies, and our lives. It is the engine that truly shrunk the world.